Good afternoon, this is Schweitzer, and we're going to run a little video here on just our introduction to limiting reactants. This is actually something that everybody knows. You use it on an everyday, daily basis. We're going to just quantify it a little more and use it in terms of chemistry. But this, again, is something that people do use all the time, and therefore, it's just a little more chemistry based here now. Okay, so let's grab a black pen. And all right, so just a non-chemistry version of kid is hired or given the task to create 50 peanut butter sandwiches. So student A brings 1 loaf of bread and a large tub of peanut butter. This is like your industrial, Costco, Sam's Club size peanut butter. And the student B brings 1 loaf of bread and 2 large tubs of peanut butter. How might you describe this situation? They're kind of a little bit lost, because when you make a sandwich, you have a little recipe or a formula or some sort of a reaction, you might say equation, where you take 1, maybe 2 slices of bread plus some peanut butter and you add it to make yourself a sandwich. But in this situation, you got enough peanut butter to use student A, for example, to make, let's say, 1,000 sandwiches. But you only have enough bread, let's say, to make 10 sandwiches. All right. So in this situation, the person needs sandwiches for 50 people. So what's student B doing? They brought more of the excess reactant, so you're only going to get 10 sandwiches. So can student B make more sandwiches than student A? No. They may have enough bread to make 2,000 sandwiches, but that doesn't help us at all because we run out of bread. So we want to think of in terms of the reactant that runs out. We call this the limiting reactant. Okay, so let's just define that a little bit better here. What is the limiting reactant? This is a situation where this reactant, or the reactant, that runs out, stopping the process. Now, we also have the excess reactant, which would be this guy, excess. And this literally is everywhere in our lives. Everything, even from doing laundry, you got a basket of dirty clothes, all right? You got a bunch of clothes in here, and you have soap, a box of soap maybe, okay? Who's the limiting factor? Are you going to run out of soap, or are you going to run out of dirty laundry? Hopefully you run out of dirty laundry first, but this is always a competition. So really a chemical reaction or a building process, a manufacturing process, is a bit of a competition. So all manufacturing situations, you're building A plus B yields C. Even if you're building sandwiches at McDonald's, you have all these ingredient pieces. And sometimes, if a piece runs out, you can still keep going. But in lots of cases, if you run out of something, then you're going to run out, you stop. Okay. Now, when we're doing an ICE table, we have initial, stoichiometric ratio, end. Just so you know that when your end hits 0, that for a reactant, that is a bingo word for that's your limiting reactant, just so you know. When your ending hits 0, that thing ran out. You can have more than one. You could run out of 2 things at the same time. They both will be limiting just fine. So let's see a couple examples of this now. So first things first, what factors in everyday life? Now again, lots of times we kind of want people to do math and show their work. This is an example where it's a little bit backwards to that. We want you to use your brain before you start using any math to think, okay, who is the limiting reactant? What factors do I want to consider? One, in anything in society, is quantity. if you're going to manufacture something, the more reactant you have, the more you can make. And then the other one is the rate used. Again, this is common math in manufacturing. Someone who works at GM or Tesla, for example, they are going to buy materials. And now cars are really starting to get more and more electric. And of course, probably a handful of years ago, BMW came out and said, we're going to be building electric cars too. But they had to secure a certain amount of raw material to make the batteries for their electric cars, or they couldn't produce them. So that's same thing Tesla, same thing GM. They're going to acquire raw materials in certain quantities based on the rate used. So they're not going to buy the same number of steering wheels as they are tires, because that wouldn't make sense. You use 4 tires for every 1 steering. We need more tires than steering wheels. That's somebody's job, probably a high-paying job too. Because if something runs out and your process stops, the company is losing money. All right, create an ice table. So we're going to do a little ice table here, but before we finish it, we want to use our brain to say, okay, who's going to run out first? A couple things to consider. Rate used. Now the rate used is just the coefficient, so this guy is the same rate used. So at that point, quantity will be the determining factor as far as who runs out first. And you should note here that at this point, equal rate used, we have less y should run first. And like I mentioned, when it hits 0, that's indicating a limiting reactant. Now, everything gets based off the limiting reactant. So I'm going to jump from here to here. As mentioned in a previous video, that arrow represents the stoichiometric ratio. I have 5 y's. For every 1 y I use, I need 1 x. I'm showing this work for a very specific purpose because that's the work required. 5x minus 5. And of course, jumping here is also 1 to 1, so that's plus 5. 1, 1, 1, 5, 5, 5. That's my stoichiometric ratio. This is going to be 5. This is 5. I had none to begin with. All right, next one. Okay, now, initial stoichiometric ratio, and who's going to run out first? I have equal quantities, but my rate used is different. Equal quantities, but this one has a higher rate used, so this is my limiting reactant. Sometimes you put the little LR above it just to indicate that's my limiting reactant. So this guy runs to 0, jump from here to here. 10x, get rid of x and go to y at a 2 to 1 ratio equals 5. So minus 5, subtract the 2, 5 left over, and 2 to 1 ratio. Everything's based off the limiting. Jumping from the y to the x would be like using peanut butter to say how much actual sandwich you're going to get when you don't consume all the peanut butter. So by going from here to here, what that is saying is that if I consume all my x, and I'm going to, how much xy will I get? If I jump from here to here, would be like saying, if I consume all my y. Now that's a big if, because you notice we don't consume all our y, but if I did, how much would I get? So it's kind of hypothetical at this point because we're not using all our y's. So everything is based off of the limiting reactant, not the excess reactant. And that's a common misconception or common problem. So I'm going to use this guy. It's a 2 to 1 ratio, same thing, plus 5. 2, 1, 1, 10, 5, 5. Okay, this is my end result. All right, now this one. Okay, initial stoichiometric ratio, and who's the limiting reactant? I got, is it x because use up twice as fast, or x because it's got less amount? This is hands down. This is slam dunk. This is going to lose 6 and go to 0. Jump to here. Okay, and at that point I have 2 to 1 ratio, so 6. Get rid of 2 x's and go to 1 y, and it's going to be 3 y's. Minus 3 is same ratio, all right, plus 3. I have 7 left. and I have 3 total. This is my answer. Again, I didn't have to do anything here that would have had to really cause me to try and figure out what the limiting reactant is. Okay. So what happens if we have a situation where, or is it ever a situation where we can't figure out the limiting reactant sort of just by inspection? The answer is yes, sometimes it can be difficult. So let's take a moment here and let's try a couple examples, at least one example where we have to actually go through a different process. Alright, so like I said, here's an example, and let's try this out. So the question is, just by inspection, who's the limiting reactant? Is it the X because it has got a smaller quantity? Or is it Y because it's got a greater rate use? And sometimes kids get a little bug in their head where they think that the quantity is more important than the rate use, and really it's not. Okay? So you might be able to do some proportions in your head a little bit, but I guarantee this is a 3-to-1 ratio. Okay? Some of us can do a 3-to-1 ratio ahead, some of us can't, but eventually we're going to get to ratios that are 1 to 32, or just some wonky ratio you're just not going to be able to do in your head. Okay? So let's try this out here once. How do I do this? Well, first of all, step 1 is, use your head, use your brain, or if you'd like, just guess. Who do you think, okay, was likely to run out first? And it doesn't matter if you're right or wrong. Let's just take this X, for example. Anybody think, okay, I think this X is going to run first. So you go run it to 0. So step 2, so just pick one essentially for our first step. And 2, just run to 0. Okay? Let's do that. Minus 125 to 0. And then step 3, just simply solve for other reactant. Jump from here to here. Now again, that's a 3-to-1 ratio, so 125 X, get rid of X and go to Y, and it's a 1 to 3 ratio. Now whenever I solve for a reactant, once again, it's a need. So this is going to say, if I consume all my X, how much Y will I need to go with it? Regardless of what I have, how much do I need? 125 times 3 is 375 minus. And you'll notice at this point, I go negative 100. And this is a problem. Okay? It's not only a problem because now I know that if I consume all of my X, my amount of Y I need is more than I have. Which means that my Y ran out a long time ago. So from this, if you ever get negative, it's not a waste of time. It just means that you picked the wrong one. This is your limiting reactant. And you need to start over. Okay, now, from this point, you should be pretty confident that you know the limiting reactant. This is my limiting reactant. And if your goal was just to figure how much Z you're going to get, then you could just simply do this, here to here. Let's do that. 275 Y's. Get rid of Y and go to Z at a 3-to-2 ratio, and that's your answer. Okay, and let's punch that in here quickly. 275 times 2 divided by 3 equals 183. Okay. So that means we're going to get 183 right there. So that means this guy went minus 275 down to 0. This should have worked. Let's go back and just figure out how much excess we have here, just because it's a common question. Jump here. Again, every time I'm using an arrow, I'm using the stoic ratio. This is a 3-to-1 ratio. Okay, so, and this would be plus 183. So I'm going to do this here, 275 Y's. Get rid of the Y and go to X at a 3-to-1 ratio. And 275 divided by 3, 275 divided by 3 equals 91.6. Let's just go 91. minus 91. So this is minus 91. And how much do I have left? 125 minus 91 is just 34. Okay, so I have 34 left. And notice how it's positive. And that is really good because that means on my math, I can't go negative on these things. And that is how we solve it using a method that maybe we don't know exactly how much we're going to get. One alternate method I'll just mention here that you could use if you wanted to. And that'd be, again, there's a lot of ways to skin a cat, but take both of these independently and solve for the amount of z you're going to get. And whoever produces the smallest amount of z would be the limiting reactant as well. And that's the amount of z that you'd actually get. So this would be like saying, if I consume all my y, how much z would I get? If I consume all my x, how much z would I get? So just an alternate method. All right, let's try another example here. Okay, so here we go. Again, a reminder, 2 factors affecting limiting reactant. Go ahead, pause this video, give this one a try. All right, so limiting reactant, equal quantities, higher rate used. This is my limiting reactant. I jump from here to here and here to here. Pretty simple 2-to-1 ratios here. So minus 50 down to 0, jump from here to here. 50 at a 2-to-1 ratio is, of course, 25. Minus 25 to a positive 25 left over. You should know why I have a smiley face there. And then here to here is the same ratio, 2 to 2, which is a 1-to-1. And that'd be plus 50. Okay? Another example. Okay? Pause the video, give it a try. So here I have a higher rate used, but I have less here, so let's try it out. I'm going to go with the aluminum on this one. So 250, 700, minus 250 down to 0. Jump from here to here. 250 at a 2 to 3 ratio is what? Well, 250 times 3 is 750, so if you divide by 2, 2 is 375. Oh, I picked wisely, I believe. 375. Now remember, that's a reactants that I need. Minus 375, which means I have 325 left over. Jumping from here to here is going to tell me how much of this I'm going to get. And that's 2-to-1 ratio. So 250 at a 2-to-1 ratio is 125 plus 125. And I got that one done. So the rest of these are just some practice problems that you should be trying. We don't do a ton of these on video. The main reason is just to show how you do it. And then your job is to move to the workbook and attempt to become proficient, checking your answers. All right, so this one, can I determine the limiting reactant? Well, I got a smaller amount and a larger rate used. So this one, without a shadow of doubt, is the limiting reactant. 1500, 15,000, minus 15,000, 0. Now again, am I 100% confident? Yes, 100%. So I'm just going to do the rest of the math here, jump over to here. And that's going to be at a 3 to 2 ratio, so 15,000. Get rid of the O2 and go to the CH3OH at a 3 to 2 ratio. So that's 2 times 15,000 is 30,000. 30,000 divided by 3 is 10,000. It's always interesting to see if you can do this in your head. CH3OH, and that's what I need. So I have 99,000 of these things. And I need 10,000, gives me 89,000 left over. Now I jump from here to here. Again, everything's based off the limiting. Okay, let's show our work here. 15,000 at the same 3:2 ratio. So that's the same one as that. This equals the CO2. So that's going to be plus 10,000. And then let's jump from here. I'm going to jump from here to here. Let's see this. For every 2 of these, I get 2 of those. So this is going to be 20,000. Okay. You just, at this point, 1:2 ratio of the CO2. Okay. One more problem done. Okay. Last one. Okay. So what does it mean to go to completion? That's a term that's going to start coming up more and more often as we come along here. What's it mean to go to completion? It means you run until something runs out. This means you have a limiting reactant, which is everything we've done so far. What's the forward reaction? Well, that means this is just a forward process. And sometimes you can have a reaction that's going both ways, but at this point, this is just kind of a little bit of a situation where we're trying to leak a few things or plant a few seeds here. So we're just going to run this reaction until this guy runs out, and this will be the limiting reactant. Just minus 50, 0, plus 50, plus 100. Okay, so a couple new terms here, things that are coming out here. Forward reaction, completion, limiting reactant. Okay. And last one we have here, I believe, and this is going to be just one more example in moles. Okay, so all the stuff we've done here so far, of course, we've done a bunch of problems in molecules, atoms. Does it work with moles too? And the answer is yes. So now, we don't do anything different, just treat the quantities. I have 16 and I have 10. And 2 and 9. Well, this guy's got a smaller quantity, this got a larger rate used, but this is like a lot larger. So I'm still thinking that this guy is going to easily be my limiting reactant. So I'm going to run this thing through in moles. 16 and 10 minus the 16 down to 0. And let's see if I was right. Okay, we're going to jump from here over to here as far as my limiting reactant is concerned. Let's do that math here. 16 O2s, get rid of the O2 and go to the C8H18 at a 9:2 ratio. Okay, 16 times 2 divided by 9 equals 3.5. Easily made it. 3.5 moles of O2, and that's needed. That's important to understand just the general idea. Minus 3.5. Which is 6.5 excess. All right. And I can just jump to everything else. This goes, now everything off the limiting, obviously. This goes to there. This one goes to there. And I will just show the work here, which is going to be 16 at a 9:16 ratio and 16 at a 9:18 ratio. So our amount we get of this will be, and this will be bigger than any of those guys, bigger than 16. This will be bigger than 16. And this will be bigger than that one, even more. Okay, so that's the 16, get all of it. It's going to be almost close to double. In fact, this guy here, answer should be 32. It's doubling 9 to 18. Okay. And this is just a little bit less than 32, probably, if I estimated, probably 28, somewhere around there. All right, and we will stop there for our limiting reactants. Move to the workbook to gain proficiency.